This is Anil Sir, and in this session, we are completely going to understand about addressing modes. Sorry, yesterday we finished already with the addressing modes, right? We are going to discuss about the ALU design. We are completely going to understand the ALU design. So once again, I welcome you all to this wonderful session in which I'm going to give you a comprehensive idea about how an ALU will be designed. So without wasting any more time, let me take you people into the session straight away. Now understand this thing. It's a very important thing to understand. Before I take you people into the session, we just need to know what are the basic components of the CPU. What are the, hi Arshita Anand, very good evening. What are the components of the CPU? The components of the CPU are register set, ALU and a control unit. Now, in which the design of the ALU plays a vital role. How the ALU is going to get designed, let us understand. So, before I take you people into the session, this is Anil Sir. About myself, this is Anil Sir. I have a 13 plus years of experience. I'm a triple PG holder. I did my MS in Information Technology, MBA. I also did my MSc in Mathematics. So, let me take you people straight away into the session. Now the thing is, you have a session coming in your way. As I'm reminding, hi Arshita, very good evening. You have a session, wonderful session, which is coming in your way. Session is going to be taken by our IIT alumni, Abhinav Negi sir, who has 10 plus years of experience. And he is going to give you all the tips and tricks. How you're going to see yourself from a beginner to a topper. Topper meaning just not any topper, just you should be topper meaning there is only one definition for that. If you are in between 0 to 100 rank, rather 100 to 0 rank, you will be considered as a topper. But anyhow, you will be given all the tips and tricks to crack the GATE exam with the best rank. So if you are aspiring for the GATE, no matter which year you are eyeing for, you will be given the complete details, the complete idea. You will be directed and you will be guided properly in this very session. Please do not miss this session, which is coming live on your way on the 19th of November, 8 p.m. So, and please download this test series. I request you people to download the test series, which is available at the very affordable prices, because this is the right time for the test series. Needless to tell you people, because here right now we people are in, at the end of the November. Till November to the January, we have only one limited time, a very limited capsule of the time in which we just have 60 to 70 odd days. This must be productively and potentially utilized by attempting as many test series as possible. So, BYJU'S Exam Prep, we are providing you as an initiative to help your students out. The test series are at very affordable prices. So make most out of this. Excuse me. Just a minute. Make the most out of the test series and just, hi Anu, very good evening. And then you'll be able to crack the GATE exam very easily, because the test series, let me tell you, is going to give you a different dimension for cracking the GATE exam, because the GATE exam you will be familiar with. The moment you attempt the test series, you will get to know what all the type of questions that you're going to get. Now, one more important thing is, this is also time for the mock test, right? The mock test will give you the idea, the basic idea, the blueprint of the paper pattern. So it is also the time for the mock test. The mock test is coming live in your way from the 15th November to 22nd November. The mock test will be live. You just give the mock test, and first of all, you just need to get registered. If you haven't already yet, do get registered to the mock test and give the mock test, and you will have to wait for the result on which is going to be announced on 23rd of this month. So these two are mandatory things. First of all, get the test series. Second thing is, do not miss the mock test at all. So let me take you people. Download the app. Yeah. Now, the today's session. Excuse me. I am going to move this side because it is behind me, I guess. Yeah, but anyhow, we are going to discuss about the arithmetic and logic unit. in the arithmetic and logic unit, let me tell you, in the arithmetic and logic unit, let me tell you, there are three different components. The first one is arithmetic unit. Second one is logic unit. And the third one is shift unit. Okay. These three units will be clubbed together because when you talk about the ALU, ALU is able to perform a wide variety of operations. The first type of the operation that can be performed by any ALU is the arithmetic operations. What are the basic arithmetic operations that can be performed by the ALU? ALU is able to perform addition, subtraction, incrementing and decrementing. ALU is also able to perform the logic operations. Logic operations are AND or NOT. There are altogether, we do have a 16 different logical operations, including set and clear. What is set? If you perform set operation on any register, all the digits of the register will be set. If you perform clear operation on any register, all the digits of a register will be cleared. That is the difference between set and clear. Okay. So finally, shift operation. What is the shift operation? Already you know. There will be right shift, there will be left shift. The contents of the register will be shifted right or will be shifted left to one bit position when you perform this shift. It could be a right shift or the left shift. Now when you talk about the ALU, ALU is a multiplexed unit of arithmetic unit, logic unit, shift unit. All these three units will be differently, designed or manufactured. Finally, all these three units will be multiplexed. This multiplexed unit of all these three units together is called an ALU. Got me? Now in which we don't need to discuss about the logic unit. Let me tell you. Let me go to the next yeah. Here, arithmetic logic and shift units. I need to position myself towards, I guess, the right or left, because it's no. I think this is that way because yeah. No, I think I am being cut. But anyhow, I will explain. Yeah. Stay focused here. Careful. I am going to write what are all the arithmetic operations that are going to be performed. There are only 4 basic arithmetic operations that are going to be performed by the ALU. What are those? Addition, second one is subtraction, and the third one is incrementing, and the fourth one is decrementing. These are the only operations performed by the ALU, not multiplication, not division, because multiplication and division are the shortcuts for addition and subtraction. If you want to perform multiplication, some addition should be performed in loop. If you want to perform subtraction, some subtraction must be performed. If you want to perform division, some subtraction must be performed in loop. And increment and decrementing are also the operations that are going to be carried out in an ALU. And similar to that, we do have addition with carry and subtraction with borrow. Okay, subtraction with borrow. Okay, these are all the operations that are going to be performed by arithmetic unit of an ALU. Now, what we're gonna do is we just gonna build all these units differently. Finally, we club all the units. That means we will start with the incrementing unit, and then we will go for an addition unit, followed by the subtraction unit, and finally we are going to design a complete unit which can perform addition, subtraction, incrementing and decrementing. Now, let us have a look at. I hope it is completely visible. Okay, it is a 4-bit ALU. It is a 4-bit ALU. See, my ALU. Excuse me, I guess I need to come this side. This is the layout is not correct. Yeah, anyhow. Yeah, I hope now it is completely visible, right? Now have a look at this. The thing is, yeah, stay focused. Now, When you want to perform addition, first of all, we need to define the operation in order to design and construct any unit. The operation that is needed to be performed is an addition. What is addition? Let us say A is the 4-bit number. A is equal to, let us say 1011. B is another 4-digit number. B is equal to 1101. Clear? Now these must be added. In order to add a 4-digit number, what do we require? Simple, understand. Least significant 2 digits must be added. 1 plus 1 is equal to 10, right? 0 here, 1 here. 1 plus 1 is equal to 10, right? 10 plus 0 is equal to 10. So 1 plus 1 plus 0 is equal to 10, 0 here, 1 here, 1 1, 0, 1, 1 1 1, 1 1. So there will be an end carry, and here once again 1 1, 1 0, 1 0, 1 1, 1 0, 1 1, 1 0, 1 1, 1 0, and 1 1 1, 1 1. So once again, yeah. Now understand carefully. See, when you look at the operation, what is being performed? Here I am adding 4-digit number. Okay. When you perform 4-digit addition, what you require is 4 full adders must be connected together. In the 4-digit addition, you must be able to collect 4 full adders together. Now understand, before I take you people any further, understand this one very carefully. The ALU, any ALU, is defined by the supporting bits. For an example, in the real-time world, we have 4-bit ALUs or 8-bit ALUs. What is a 4-bit ALU? A 4-bit ALU can perform a 4-bit addition at a time. For an example, you want to perform a 16-bit addition. So A is a 16-digit number, B also is another 16-digit number. But if it is being carried out in a 4-bit ALU, all these total 16 digits will be divided into 4, 4, 4, 4. Least significant 4 digits will be added to B in the first phase, and next 4 digits will be added in the second phase, next 4 digits will be added in the third phase, next 4 digits will be added in the fourth phase. So by using a 4-bit ALU, if you want to perform a 16-bit addition, that will get carried out in 4 phases. Least significant 4 digits, next 4 digits, next 4 digits, and the next 4 digits. What we are witnessing right now on the screen is a 4-bit ALU and a 4-bit adder. Now let us have a look at, in this what we are going to do is, see, least significant 2 digits will be applied to the first full adder, and C0 will definitely be equal to 0, right? ALU can perform operation on 4-bit data at a time. Our ALU, right? If it is the 8-bit ALU, 8-bit ALU can perform addition on 8 bits at a time. But now we are discussing only 4-bit in order to make the things very simple. Now, let us say this is an intermediate stage, because there will be total 4 stages. Let us say we are performing a 16-bit addition. This 16-bit addition must be performed in 4 stages. Now understand, if it is an intermediate stage, this C0 will be collected from the previous stage. C4 will be connected to the next stage. If it is the first stage, C0 will be 0. If it is the final stage, the produced C4 is the end carry. Okay, so understand this. Anyhow, we are not performing 16-bit addition. Let us, in order to keep the things simple, let us keep the discussion only for adding 4 digits. Initially, A will be equal to 1. Rather, least these 2 digits will be applied here. These 2 digits will be applied here. This here. These 3 digits. Excuse me. From the next section, we got A1 and B1, and this carry will be given here. Yes or no? Similarly, these 2 digits will be applied here. The carry will be given here, and finally A3 and B3 will be connected here. So let me clear this and explain you for one more time. So A0 and B0, the least significant 2 digits will be applied here, and C0 will be equal to 0. These 2 digits will be added sum will be produced here, carry will be given to the next stage. So this full adder will perform an addition in between carry 1, A1 and B1. All three together will get added and sum 1 will get produced here. The carry 2 will be given to the next stage of the full adder, So in the next full adder, C2, A2, B2 will get added, sum will be here, carry will be here. In the next full adder, of course, A3, B3 and C3 will get added and sum will be produced here, carry will be produced here. This is what the addition is all about. So this circuit is the adder circuit. This circuit can simply perform only addition. But what if we want to correct 4 parts of operation? 3 inputs, sum, carry, outputs. Exactly what you told is right, I know. Next thing is we going to discuss about adder subtractor units. We are going to discuss about adder subtractor unit. How adder subtractor unit is going to be designed and discussed, understand. Okay, see, in the adder subtractor unit, of course, this unit is similar to the addition unit, adder unit only with a one slightest difference. What is the slightest difference? Let us have a look at. There are 4 full adders and all the full adders, first input is equal to A. Okay. And the second input, if you can have a look at, B is not directly connected to the full adder. B is connected to the full adder via an XOR gate. Yes or no? There are 4 XOR gates. To the XOR gate, B is connected. And the XOR gate second input is taken from a line M. Just once again, have a look at. There are 4 full adders. Full adder require 3 inputs. One input is from A. One more input is from the digit M. This is the carry in, right? Okay, carry is actually taken from a digit called M. Okay, now the third input of the full adder, just have a look at. One input is A, one more is carry. The third input, which has to be collected from B, has actually been taken from an XOR gate. V, of course, this is A. This must be from B, right? But we did not connect it directly. Rather, B is connected to an XOR gate. The output of the XOR gate is connected to the full adder. Here also, B1 is connected to the XOR gate. Output of the XOR gate is connected to the full adder. B2 is connected to the XOR gate. Output of the XOR gate is connected to the full adder. B3 is connected to the XOR gate. Output of the XOR gate is connected to the full adder. Now, how the circuit will be able to perform addition? How the circuit will be able to perform the subtraction? For that, understand, the XOR gate second input is taken from the bit M. Yes or no? The M is providing 2 inputs. One is carry, one more is second input of the XOR gate. In this slide, let me explain you one simple rule. When M is equal to 0, circuit will be able to perform addition. When M is equal to 1, circuit will be able to perform subtraction. Clear? Why? Simple. When you perform A plus B, what is needed to be performed? Simple. Full adder must add A and XOR gate output must only be B. So simple. Whenever M is equal to 0, one input of the XOR gate is equal to 0. When one input of the XOR gate is 0, the output will be the other input's value only. Let us have a truth table of XOR gate. XOR gate truth table, if you can have a look at, 0, 0, 0, 0, 1, 1. So whenever one input of the XOR gate is equal to 0, the output is the other input only. The other input will be produced as an output. In this rule, what will happen? Whenever M is equal to 0, XOR gate will give the output from the B digit only. What will happen at that time? The full adder, it is receiving one input from A, one more input is from the XOR, which is equal to B. So A plus B is being performed. Now, whenever M is equal to 1, what is going to happen? Whenever M is equal to 1, the XOR gate, the circuit is going to perform subtraction operation. Why? Let us have a look at how A minus B is going to be performed. A minus B is equal to A plus 2's complement of B, right? This is 2's complement of B. What is 2's complement of B? B is 1's complement plus 1. So A minus B is equal to A plus B complement plus 1. This is the rule of the subtraction. So in this slide, understand, whenever M is equal to 1, what exactly is going to happen? Anyhow, we are not touching A. Only B will get altered. One input of the XOR gate will be equal to 1. Whenever one input of the XOR gate is set to 1, output is other inputs complement. Once again, let us have the truth table of the XOR gate. XOR gate truth table 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. Look at the last two digits, last two values. Whenever one input of the XOR gate is 1, is said to be 1, the output is next inputs complement. Got me? So 1, 0, 1. What is 1? 0's complement. 1, 1, 0. What is 0? 1's complement. So whenever one input of the XOR gate is equal to 1, output is other inputs complement. Got me? Complement only, not 0. So at that case, what is going to happen? Our circuit is going to perform, our circuit is going to perform A plus B complement. Yes or no? This is A. As one input of the XOR gate is equal to 1, all XOR gates will give you B complement. Okay. And as M is equal to 1, it also makes C0 equal to 1. What exactly is getting performed? A plus B's complement plus 1. So A minus B is equal to A plus B's complement plus 1 exactly is operation of A minus B. So whenever M is equal to 1, this circuit is going to perform subtraction. Okay. So same circuit is performing two operations: 0 addition, 1 subtraction. Okay. Next, already explained this. Incrementer is simple. What is incrementing? Incrementing can be done very simply by adding 4 half adders together. In order to simply perform incrementing, I don't require full adder. I require only half adder. Yes or no? Why? Because let us have a look at A is equal to, let us say 1, 0, 1, 1. During the incrementing, we will add 1 to the total value. What is going to happen? 1, 1, 0, 1, 1 here, 0 here, 1, 1, 0 here, 1 here, clear. 1, 0, 1 and 0 is the carry, 0, 1, 1. At any point of period, we are just only adding 2 digits. 2-digit addition. Once again, understand, during the addition, at every bit, we require to, at every addition, we require to add 3 digits. One is from A, one more is from B, one more is from carry. But during the increment, we will only one operand digits. Second digit will always be carry. Got me? So during an increment, we require to add at any point only 2 digits. For 2-digit addition, we don't require a full adder. We just require a half adder only. So again, in a 4-bit ALU, it will be able to perform only a 4-bit incrementing. For that, I require to connect 4 half adders together. So simple. The mechanism is very simple. There are 2 inputs, X and Y. X input is always from A, A0, A1, A2, A3. One input of the half adder will always be A. Second input of the half adder. Second input of the first half adder, that is the least half adder, will be equal to 1 because 1 is going to be added to A0. So here A0 plus 1 is going to produce a sum and there is a carry. The carry will be the second input of the second half adder because every half adder requires 2 inputs. One is from A, one more is from the carry of the previous bit addition. So carry will be connected here and A1 is the next digit. A1 plus this C0, I would say. A1 plus C0 will get connected, will be added. Sum will be produced here, carry will be produced here. So this is C1. A2 plus C1 will get added, sum 2 will get produced here, carry will be added. A3 plus carry will be, the S3 will be here, C4 will be here. This circuit will simply be able to perform what? Incrementing operation. Finally, what we're going to do is, we are going to design a circuit which is going to perform, am I here? Are you here? Yeah. In this circuit, we are going to see, this is a circuit. What you're witnessing on the screen is a circuit which is going to perform addition, subtraction, incrementing and decrementing. So ALU main part is the arithmetic unit, right? This circuit will totally perform all the operations. So far what we have done, initially we perform addition operation. Next we designed a circuit to perform addition plus subtraction. Then we design one incremental unit. Finally, we need to design a unit which can perform addition, subtraction, incrementing and decrementing. How? Let us completely have a look at. In order to demonstrate this circuit, stay focused carefully. In order to demonstrate this circuit, first of all understand it is a 4-bit ALU. A 4-bit ALU arithmetic units will have 4 full adders. Full adder 1, full adder 2, full adder 3 and full adder 4. All these full adders will require 3 inputs. Stay focused. Full adder's first input is from A. Have a look at this. There are 3 inputs. This is the first input. There will be a second input. Second input I did not show it. First input is from A. Okay, look at this. There are 4 digits of A. I would say A is equal to 1011. Least significant digit A0. Next A1. This is A2. This is A3. A0, A1, A2, A3 are connected to first full adder, second full adder, third full adder, fourth full adder as the first input. You can see A0 is connected here, A1 is connected here, A2 is connected here, A3 is connected here. That means that every full adder first input is taken from the digits of A. Okay. Now, second input is not shown. Third input is shown here. Third input is from the external carry digit. This external carry digit exactly producing the third input. Okay. Now, what is the second input? Second input is not the second input has to be from B, right? But B is not directly connected. B actually is connected to the full adder via a multiplexer. The second input of the full adder, GATE CSE ka. Yes, sir, batch ka start. Which batch you're talking about, Sandeep? Which batch you're talking about? If you can precisely ask me, I will ask you. Is it the app batch or the YouTube batch? Sandeep, ask me precisely so that I will be able to answer. Now, second input of the full adder is the output of the multiplexer. It is already started. We are in the middle of that. Now the thing what's happening is the computer architecture and organization. Okay. So anyhow, not only this, we are coming up with a multiple sessions. This is one quick revision session, complete revision session. Okay. This is the crash course. Right then we come up with what you call, there are some other plans. We're going to tell you. So from this month to the next month, we are planning, we already planned a crash course which is being executed right now. Then we will come up with the marathon sessions. So do follow the YouTube channel regularly and carefully so that you will be able to crack. Anyhow, we are in the middle of the COA and the next session, I guess it is like computer networks. I don't exactly know. I will let you know what is the next subject. Okay. Yeah. Now, anyhow, see, one input of the full adder is from A, one more input from multiplexer, one more input from is the C. Now, when you look at the multiplexer is a 4x1 multiplexer. This 4x1 multiplexer requires 4 inputs. What are those 4 inputs? When you look at the multiplexer, I am drawing a blueprint of one multiplexer. Okay. A 4 into 1 multiplexer, see, any multiplexer of these will have 4 inputs. 1, 2, 3, 4. The first input is B. Second input is B's complement. Third input is 0. Fourth input is 1. Look at this. First input is from B. Second input is B's complement. Third one is a 0. Whether you are able to see this or not, the third input is 0. Fourth input is 1. Similarly, go to the second multiplexer. The first input of the second multiplexer is B. The second input of the second multiplexer is B complement. Yes. The third input of the multiplexer is 0. Fourth input of the multiplexer is 1. Similarly, B complement, 0, 1. Similarly, B complement, and it is a 0 and it is 1. Clear? Okay. Stay focused and understand. Simple. If you understood so far, next, in order to understand operation, it is even more simple. There are common selection inputs to the multiplexer. Which input is going to be enabled from the multiplexer side will be defined by the common selection inputs. You can see the selection inputs S0, S1. Okay. S0, S1. No, it is not AB01. Anuvaja, understand. Multiplexer is not connected from A input. XR is only connected, the full adder is only connected from the A input. You can see A input is neither directly connected to anything, rather A input is never connected to the multiplexer directly. The A input, when you look at, it is directly connected to the full adder. A is not bypassed. A is not connected via any channel. A is directly connected to the full adder. Yes or no? Agreed or not? Only B has been connected to the multiplexer. The output of the multiplexer is connected to the full adder. This is precise to understand. Okay. So, now then, let us understand. These are the selection inputs. These selection inputs are the common selection inputs to all the multiplexers. You can clearly see the selection inputs of the multiplexer are commonly taken from these selection lines. These selection lines. Okay, that means that the selection inputs are uniform to all the multiplexers. If the selection inputs are equal to 0, 0, then all the multiplexer selection inputs will be equal to 0, 0. Now I will tell you how the circuit will be able to perform addition, subtraction, incrementing and decrementing. So stay focused. When the selection inputs are, okay, fine. When the selection inputs are 0, 0, what will happen? Addition will get performed. Why? Because, see, multiplexer output is equal to B. Multiplexer will enable the first input of it. All the first inputs of the multiplexer, needless to say, is B result, right? Yes or no? Multiplexer, whenever it receives the selection inputs is equal to 0, 0, all the multiplexers will enable their first input. The first input of all the multiplexer are the B digits only, B0, B1, B2, B3. Now what will happen? The full adder is going to perform the addition in between A, because A is already connected, and B. So during S1, S0, selection inputs are 0, 0, then the circuit is going to perform addition. And whenever S1 and S0 are equal to 0, 1, what is going to happen? Subtraction is going to happen. Why? Logic is very simple. Because whenever selection inputs are equal to 0, 1, what is going to happen? I will erase this. Multiplexer output is the second input, right? Selection inputs are 0, 1. Second input will get enabled. What is the second input? Second input of the full adder is, second input of the multiplexer is B's complement. Will crash course cover entire syllabus? Crash course covers important topics. because within 4 days or 5 days, entire syllabus coverage is a myth. But the important topics will be covered. But crash course is supported by many courses that are coming up for you guys. You don't need to worry only about the crash course. Crash course is going to cover the important topics. Right then we are going to come up with the marathon sessions. In the marathon sessions, we are going to make the total topic as comprehensive. Okay. Now stay here. 0, 1 meaning the second input of the multiplexer is B complement. This is B0 complement, B1 complement, B2's complement and B3's complement. Okay. So all the B's complemented digits will be bypassed. So full adder is going to perform A plus B's complement. Okay. But in order to perform subtraction, I need to perform A plus B's complement plus 1. A plus 2's complement of B is exactly equal to A minus B, right? So in order to make it A plus B's complement plus 1, what I will do is I will set the C in digit is equal to 1, because in the full adder, A is one input, B's complement is second input. A plus B's complement is only half done. We need to perform one more addition of one digit. That one digit, that value 1 will be given from C in. Whenever C in is equal to 1 and S1, S0 is equal to 0, 1, the total circuit is going to perform subtraction. Okay. And the simple, needless to say, whenever S1 and S0 are equal to 1, 0, what will happen? The XOR gate third input will get enabled. The third input of the XOR gate is equal to 0. The third input of the XOR gate is equal to 0. 0 will be enabled, third input will be enabled and will be connected to the full adder. So full adder already got A, and the second input is coming from the multiplexer. The multiplexer enabled the third input. The third input is 0, right? So the third input will be equal to 0. The 0 is bypassed and connected to the full adder. So the full adder is going to perform A plus 0. A plus 0 does not alter the value of A. So in order to make it A plus 1, C in value, which is carry in digit, which is connected as the third input to the full adder, must be set to 1. So at that time, A plus 0 plus 1 will be performed. So here increment operation is getting performed. Alright. Next thing, we have only one operation, that is decrement operation. Now the thing is, whenever S1 and S0 is equal to 1, 1, what will happen? The final input of the XOR gate will get enabled. What is the final input? The final input of the XOR gate is equal to 1. So XOR gate enable 1 and will send it to the full adder. Full adder is going to receive 1 from all the multiplexers. So here what is happening? A value, let us say it is 1011, being added to 4 ones here. So how adding 4 ones to A is going to decrement the value of A? Understand carefully. This is the shortcut of decrementing. Stay focused and write it down somewhere. When you want to decrement any register's contents, only the thing is you should be able to add those many ones which is equal to the number of digits of the register. For an example, I have a 4-bit register. If you want to decrement the 4-bit register value, you need to add 4 ones to the 4-bit register. There is a 6-bit register. You need to add 6 1 to the 6-digit register in order to perform decrementing. How it is going to happen? Understand. There is a value. There is register A. Register A is equal to 1111. When you decrement it, what will happen? 1111 minus 1 is equal to 1110. This is how decrement is going to get performed, right? But this is a regular decrementing. But in the computer system, when you want to decrement, what will happen is, to the 4-bit value, 4 ones will be added. Here 1 plus 1 is equal to 10, 111, 11, 111, 11, 111, 11. If you discard the end carry, 1110 is the exact value when you subtract a 1 from 1111. Now I am going to take one more example. Let us say I want to subtract 1011. 1011 must be subtracted. 1011 minus 1 is equal to 1010, right? We'll see if this is going to work or not. Okay, so 1010 must be added with 1111. Clear? So what exactly is going to happen at that time? See, 0 minus 1 not possible. 10 minus 1 is equal to 1, and yes or no? 10 minus 1 is equal to sorry, bigger pardon. We are not performing. Excuse me. Got it. Yeah. 1010 we need to perform addition with 1111. 011 11 11 10. Excuse me, what was the value that I suggested? I guess it is 1011, right? Yeah, 1011 minus 1, bigger pardon, I lost the track. 1011 minus 1 is equal to 1 minus 1, 0. It is 1, it is 0, it is 1. So it must be the value. So what we need to do is, to 1011, we should add 1111, 4 ones. So 11, 0, yes, 111, 11, 11, 0, 1, 111. 1 1. So either you add 4 ones or you decrement or you subtract a 1. The things will be pretty same. So in order to perform the decrementing operation, we should be able to add 4 ones to a 4-digit value. If it is a 6-digit value, you should be able to add 6 digits. So here, by the same rule, what we are doing is, whenever selection inputs are, excuse me. Yeah. S1 and S0 is equal to, 1 1. The final input will get enabled. What is the final input? The final input is always equal to 1. Okay. So already in the Fulado, this is 1, this is 1, this is 1, this is 1. Already in the Fulado, A value is available. This is A0, A1, A2 and A3. Now all will get added with 4 ones so that decrement operation will get performed. But here we need to understand why exactly decrement operation is being performed when we add those ones. Reason is very simple, because in the computer system, when you want to perform A minus B will be performed as A plus 2's complement of B, right? A plus B's complement plus 1 with this operation. So now thing is, let us say I want to perform a decrement operation 1011 minus 1. Did you get it? Now here this 1 will be considered as B. B will be equal to 0001. Yes or no? A is equal to 1011 should be subtracted. Rather, a 1 must be subtracted from 1011. So B becomes 0001. Now we need to convert this into its 2's complement. Initially, please convert it into 1's complement. 1's complement of 0001 is equal to 1110. This is 1's complement. 2's complement of 1110 is equal to 1's complement plus 1. That is equal to 1111. This is the reason why whenever you want to subtract a 1, finally we will get 1111. Okay. So this is the 2's complement of B, which is equal to 0001. So when 1111 gets added, actually we are performing A plus B's complement plus 1, 2's complement of B only, right? We are not moving anywhere outside. We are exactly confined to the semantics of the processor. I hope I made my point very clear here. Even decrementing also is equal to subtraction. Subtraction, there is only way possible. First of all, we need to take the subtrahend, we need to convert it into 2's complement, then add it to the minion. So minion plus subtrahend's 2's complement plus 1, subtrahend's 2's complement will be giving you A minus B, as simple as this. Okay, with this, we have designed an arithmetic unit of the system. Understand carefully. understand carefully, this arithmetic unit is capable of performing addition, subtraction, incrementing, decrementing. But for this, the multiplexer inputs must be equal to, for the addition, it must be 0, 0. Selection inputs I am talking about. S1, S0 must be equal to 0, 0. And S1, S0 must be equal to 0, 1 for subtraction. Okay. And S1, S0 must be equal to 1, 0. Whenever S1, S0 are equal to 0, 0, this circuit is going to perform addition. Whenever it is equal to 0, 1, subtraction is going to get performed. Whenever it is equal to 1, 0, incrementing will get performed. Whenever S1 and S0 are equal to 1, 1, decrement operation is going to get performed. Clear? Now, hold on. We did not completely finish it. As I told you, let me go back. See, the ALU is a multiplexed unit of arithmetic units, logic units, and shift units. Okay, how to design logic unit and shift unit? We don't need to worry. We do not need any different, the design mechanism. The design mechanism can be very simple for logic unit and shift unit. For performing shift, it is even more simple. Use a shift register. Use a shift register. And for designing the logic unit, understand there are 16 logic operations. Each and every logic operation is supported by a corresponding gate, except a few logic operations. Let us some logic operations are clear and set. For this, we don't need any gates, rather some other mechanism is actually required. For that, understand carefully how to design the logic unit. All the 16 operations must be multiplexed. I will use a 16 into 1 multiplexer. All the corresponding gates will be connected as the inputs to this multiplexer. Then there will be output generated from one of the inputs. Let us say this is AND, this is OR, this is NOT. So a logic unit of an ALU is the multiplexed unit of all the logic operations. Now, what is the shift operation? In order to perform the shift operation, I just require to use the shift register. Now, let me show you the complete ALU. The complete ALU is the multiplexed unit. It's the 4 into 1 multiplexed unit. Okay, it requires 4 inputs. Okay. Now, if you remember, I have 3 units in the system. One is arithmetic unit. The arithmetic unit output is connected to the first input of the multiplexer. The logic unit output is connected to the second input of the multiplexer. And shift right, I will use the shift right shift register that will be connected to the third input of the multiplexer. Got me? Shift left, that will be connected to the fourth input of the multiplexer. Now, this is my design of the ALU. The ALU will take 4 inputs. It's a multiplexed unit, 4 into 1 multiplexer. Once again, first input is from the arithmetic unit. What is arithmetic unit? Just a short while ago, we designed the total arithmetic unit. The output of the arithmetic unit is connected to a 4 into 1 multiplexer, which is the final multiplexer of the ALU. The output of the logic unit is connected to, again, the 4 into 1 multiplexer. Similarly, shift right and shift left. So, this is my total ALU, which is going to perform all the operations, any operation one at a time. It can perform, if I'm an ALU, I can perform a wide variety of operations. I can perform 6 arithmetic operations: addition, subtraction, incrementing and decrementing, addition with carry, subtraction with borrow. 16 logic operations, 2 shift operations, right shift and left shift, but only one at a time. I can't execute multiple operations. ALU can perform any operation from arithmetic, logic, shift right, shift left, but only one at a time. Okay, so with which we have come to an end of this session. I hope you got it comprehensively understood. till the way I intended you people to understand. Okay. I request you people to like and share the session and subscribe to this channel if you haven't already yet. Unless you do have any follow-up questions, Anil Sir is gonna sign off. Thank you so much, and that's it from the session. If you do have any doubts, ask me right now in the next 2 minutes. Otherwise, we're going to, finish this session straight away. But once again, let me admit firmly, it is the time for you people to get the mock test. Mock test is on your way from 15th of this month to 22nd of this month. Please attempt this mock test without fail. This mock test is very important in deciding your GATE rank. When you give this mock test, you will be able to know where exactly you are standing in. You will be able to clear or cover all the loose ends. You will be able to prepare well, and then you will be able to get a very good rank in the GATE. Okay. So, and one more thing is, there is one excellent session from Abhinav Negi Sir is coming on your way live from 24th of this month at 8 p.m. So don't miss this opportunity, because you are going to get every tip and trick in the world to crack the GATE exam. Okay. Chinmay, all the operations performed. Operations are not performed using multiplexers. Do not get operations, sir. Understand, are performed in full adder only, right? Operations will be performed in the full adder if it is the arithmetic unit. Operations will be performed in the gates, it is the logic unit. But multiplexer will select only one operation. Understand? Did you get my point? Let us look at this unit. Stay focused. Look at this unit. See, this multiplexer can select one of the B inputs. Got me? So, according to the multiplexer's inputs, one operation will be performed. Got me? The full adder, if it receives B, A plus B will get performed. Okay. If it receives B's complement, A plus B's complement will get performed. So, in order to make it A minus B, we will add a 1 from Cn. We will make Cn is equal to 1. So, A plus B's complement plus 1, needless to say, A minus B. Did you get it? Multiplexer is not performing any operations. Rather, even for logical, stay focused. Even for logical, see, there is like an OR gate. There is an OR gate. There is an AND gate. Okay. There is an XOR gate. And there is a NOT gate. I hope you got my point. Okay. Now, understand, I have two inputs. One is A, one more is B. A and B are applied to all the gates. But for the NOT gate, only A will be connected. Now it is the selection inputs of this multiplexer, S1, S0, will define and decide which operation is to be performed. Did you get it? Now S1 and S0 are equal to 0, 0. The multiplexer is going to perform what you call OR operation. Multiplexer is going to enable OR operation, because understand, OR operation is being only performed in the OR gate, but the multiplexer is selecting the OR operation. Did I make my point very clear? Chinmay, multiplexer is not just, it's only for selection. Already I am a multiplexer. I am receiving 4 inputs. One is from OR, one is from AND, one is from XOR, and one more is from NOT. According to my selection inputs, the operations are already performed and the outputs are available at my inputs. I will select one input, I will send as an output. Got my point? I am not performing any operation rather than selection. Did you get it? Chinmay, do I have you with me? Is your doubt clarified? Okay. So we need 16 into 1 multiplexers for performing all logical operations on yes. Correct? What you told is correct. Here, you spotted a very good point even before I tell you. We need 4 stages, right? We need 4 stages. But actually, because of the limitation of the screen, we are just able to see only one stage. Like that, we require 3 more stages. I hope you got that point already, right? Absolutely, you are correct. Absolutely, you are correct. You are perfectly spot on. Anu Ajay, did you get his point? Here, yes, there are, let us say, A is a 4-bit value, B is a 4-digit value. Now, like this, I require, 4 more stages, right? Here we'll be able to show only one stage of the ALU. Okay, like that, but there are different stages. This is only for the first digit, A0, B0. But there is A1 still. Let me erase this. Okay, A0, B0. For A0, B0, this is the first multiplexer. But still, there is A1, B1. Still, there is A2, B2. Still, there is A3, B3. Okay, so what Chinmay spotted is perfectly spot on. Due to this constraint of this, the space limitation, we just are able to showcase, we just are able to demonstrate or manifest only one stage of the ALU. Got my point? What Chinmay told is perfectly right. So with this, we have come to an end of this session. Did you get this, Chinmay? Can we sign off? Can we sign off? Please respond. Yeah, that's it from the session. Thank you so much. Anil Sir signing off. Thank you, Anu. Thank you, Chinmay, for joining.